Hello everyone. This is the third section of tutorial 0, and in this section I would like to introduce STAN to you. STAN is a statistical modeling language and can help us do Bayesian analysis in a more efficient way, although it's still kind of complicated. Used to it, well, you will figure out that it's not hard at all. In this tutorial, I will focus on the big picture of coding a STEM program, and in future lectures, you will learn about the details of different models. I will use STAN to do a very simple linear regression model and compare it with LM function in base R. And again, I will use the iris dataset and let the x to be sample width and y be the sample length. The LM function is pretty simple. You just plug the data into it and set the y and x in the function. And then we get the result. So the intercept is 6.5 and the slope is negative 0.2. It was very simple to do the prediction. And firstly, you need to create a data frame containing the x value. And I also put the y value here just for plotting. And then you just need to put the model we have fitted into the predict function with the data frame we have created. And then you can get the result. If you want to get the confidence interval, you just need to set the interval parameters in the predict function to confidence and set the level to what kind of region you want. But be careful that the result of confidence interval will be a 3-column data frame. The first column is the fitted mean value, and the second is the lower bound, and the third column is the upper bound. So you need to filter out the lower bound here, and upper bound here. To visualize the result, I will use the ggplot functions we've learned in the previous section. So firstly, I just put the backtest data frame into a ggplot function, and then firstly, the first layer of our plot is the true value, and I will illustrate it in using the scatter plot. So here are the true values, and for our prediction value, since it is a regression line, I will use a line plot. You can see this red line will be the prediction values of our model. And then for the third part is the confidence interval. I use the ribbon function we've learned in previous section and set the lower bound to the y mean and upper bound to y max. And the result will be like this. And you may wonder why I set color equal to LM and field to LM as well in these two lines. And it's for easier comparison for later plot. Process are very similar. So firstly, we have to write down the statistical model and then feed the data into the model, and thirdly, and do a prediction and calculate the confidence interval. No preference is to write down the STAN model in other text editors like Sublime Text. So a STEM program has 3 required blocks: data, parameters, and model. There are 4 other optional blocks in STEM as well, and they are function, transform data, transform parameters, and generated quantities. The functions block is where you declare a customized function. And notice that the functions block, if you include it in a STEM model, it must be the first block. And the transform data block will not be taught in this class. The transform parameters block will be taught in future class. The generated quantities block is the place for you to do prediction, and it will be taught later in this section. The syntax in STAN is more like C++, so you need to declare the data types, their dimensions at the beginning. First, it's the integer n. It represents the length of our data, like how many rows are there in the data set. And secondly, it's real, which is the floating number data type in STAN, and our x will be a n length real vector, and it's the same for the parameter block is where you indicate the parameters you want to estimate. For a linear regression model, we will want to estimate the intercept, the slopes, and the standard deviation of the errors around the regression line. These 3 parameters are all floating numbers, so we set them all to real data type, and alpha is our intercept, beta is our slope, and sigma is the error term. Notice that sigma must be a positive number, so I set the lower bound equal to 0 here, and this will help the sampling in STEM. Log is the core of the STEM program. We have to specify the likelihood function of the statistics model we use and the prior distribution of the parameters we want to estimate. And for a linear regression model, we assume that the y will be equal to intercept plus coefficient times x and plus the error term, with the error term follows a normal distribution centered at 0 with the standard deviation equal to sigma. For the prior distribution, we just assume that all three variables comes from a standard normal distribution, except that the sigma value will only be the right-hand side of the normal distribution since the lower bound of sigma is 0. Generated quantities block, I would like to do the prediction for each x. So firstly, I will declare the prediction y. And then I would like to do the prediction using the normal RNG function. The normal RNG function will draw a random sample from the normal distribution with the parameters we provide. So in this example, the parameters will be calculated as what we model it. So we've just completed our first STEM model. In the future classes, we may go through different kind of model besides regression, and we will learn about more kind of prior distribution and other details of different models. We just copy and paste the STEM model we constructed in the Sublime text and create the data input for the STEM model. So here we have one integer n and one vector x and one vector y. So we put n, x, and y into a list. And n will be the number of rows of this data set, and x will be the sample width, y be the sample length. And then we can call the STEM function and assign the model code to the model we just wrote and the data to the list we've constructed, and then run this line. After STEM complete its sampling processes, we can check the parameters value by just running the STEMFit object. So we can see the alpha, which is the intercept, is 6.45, and beta has a mean at negative 0.2, and it's pretty close to what we've gotten from the LM function. There are some more functions for us to get better understanding of our STEM model. First, if we just want to get the mean of each parameters, we can use the get posterior mean function, and we can set the parse parameters in the function to tell the function which parameters we are interested in, because maybe we don't want to show all the predicted y values, which are very messy. You can set alpha, beta, sigma in the parse. If you want to get full summary of the STEM model, you can use either summary lm.fit or print fit. So first we can check print fit, and the result is very similar to just run the lm.fit function. But the difference is that you can also input parse or props to control which parameters to show in the print screen, and also the confidence interval in the model. For example, if we want to know about the median of alpha, we can type. So by running this code, you can see the mean value, the 50% interval, which is the median. Using print function, this result will not be saved, and if you want the result to be stored into a data frame, you need to use the summary function. And again, you can also use the parse and props parameters to control the output. The result will be a list of length 2, and in the first element of the list, it's the cross-chain summary, and in the second element, it's the chain-by-chain summary. You will learn about what is a chain means in future class, so don't worry about that. We just need to use the cross-chain summary. As I mentioned before, the result of MCMC will be thousands of samples, and if we want to get all the samples, you can use the s.data.frame function, and the result will be like this. So each row represents one iteration or one sample in the MCMC result. And in the STEM function, actually, we can set how many iteration we want by the ITER parameters. So the default iteration is 4,000 iterations. So we can see we have 4,000 rows in the LM fit. Last step is to make the prediction and calculate the confidence interval. And actually, the calculation of prediction has already been done in STAN, and we just need to get it from the summary report. So the first method is to call the summary function and set the parameters to our prediction value and set the probabilities to the confidence intervals we want. And don't forget to choose the first element in the result. So we will get a result like this, and we can use the as the data.frame function and to make it more useful. The result will look like this, and we only need the mean and 2.5% and 97.5%, these three columns. So we can use the select function we learned and type mean and 2.5%. Don't forget you need to put the 2.5% column name in a back quote since there is numeric values. And put the original data used by using mutate. So the result will be like this with the mean and confidence interval and original data. Other method is to calculate the mean and confidence intervals by the samples we have. And notice that I store the samples in the post data frame, and we can get the results by apply the mean function and the pi, which represents percentage interval function on the post data. Is that the result of the pi function has two rows, so I need to add this part to select the lower bound or the upper bound. I add the columns of original data, sample width and sample length to the prediction 2 data frame as well, and we can compare the result of these two methods, and you can see that they are all identical. The last thing we have to do is to plug the result from STAN against the result from the LM function. Again, we will use the geometric line and geometric ribbon function, and the only different thing is that we need to reassign the data to be prediction 1 here, or otherwise the geometric line function will by default use the data we provided to comparison this plot, and which is the result from LM function. The result will be like this. You can see that the prediction line are almost identical, and the prediction intervals are quite similar as well.